Hello and welcome. In this lesson, we will discuss the importance of the volume mesh and learn different fill with methods for generating the volume mesh. We will dig into finer details of these methods and understand the user inputs required. Finally, we will understand the importance of the volume mesh quality and learn how to improve it in the Ansys Fluent meshing watertight geometry workflow. Let's get started. Volume mesh generation is the process of discretizing or representing a computational model using a large number of discrete volumes or cells, within which the governing equations are solved. Extreme care needs to be taken during this process, as the volume mesh has a significant influence not only on the accuracy and convergence of the solution but also on the total simulation time. To generate the volume mesh, there is a dedicated task in the watertight geometry workflow, that is, the generate the volume mesh, which can be used to define specific meshing requirements. Let us understand this task using a demo problem. Launch Ansys Fluent in meshing mode. Go to File, Read, and select Mesh, and then pick the provided mesh file. Once Fluent finishes reading the file, you will notice that the watertight geometry workflow has been automatically set up till the Add Boundary Layers task. The model we have here is that of a generic two-element rear wing found on a Formula Series type race car enclosed within a virtual wind tunnel. Except for the inlet and the outlet, all the other sides of the wind tunnel and the wing geometry are considered as walls. The model consists of only the fluid domain, with the wing considered as a void. In the Generate the Volume Mesh task, the first option is the Fill With. There are 4 different methods available, namely polyhedra, tetrahedral, hexcore, and poly-hexcore. Basically, the names of these methods represent the geometry or the shape of the cells that are used while generating the volume mesh. Based on the selection, a list of inputs is populated below this option. Let's look at tetrahedral fill with method now. When the fill with option is set to tetrahedral, the user is prompted with growth rate and max cell length inputs. As the name suggests, the growth rate is simply the length-based size ratio of the next cell to the previous cell as viewed away from the boundary or the boundary layer cap towards the interior of the domain. By default, the value is 1.2. The next input is the max cell length that defines the size of the largest cell in the domain. By default, Fluent automatically calculates this value depending on the existing surface mesh of the computational model. However, the user can change the value as required. For this demo, let's keep the default values for these user inputs. Click on the Generate the Volume Mesh button. Once the volume mesh has been generated, we can turn on the clipping plane and visualize the Y-cut of our mesh. Notice that the volume is filled with tetrahedral cells and the prism layers are created along the wall surfaces from the triangular surface mesh, as can be seen here. This mesh has approximately 2.5 million cells and the minimum orthogonal quality is 0.15. The major advantage of tetrahedral mesh is its flexibility and adaptability with complex geometries. It is generally recommended to use prism layers to avoid highly skewed tetrahedral cells at the wall boundaries and to reduce the overall high cell count. Let's look at polyhedra fill with method now. When the fill with option is set to polyhedra, which is the default option, the user is prompted with the same basic user inputs as in the case of tetrahedral fill with method. With the default settings and the same surface mesh, let's generate the volume mesh for our demo problem. Notice that in addition to the volume being filled with poly cells, the triangular surface mesh has now been modified to create a polyhedral surface mesh from which prism layers are grown into the computational domain. The mesh has around 0.56 million cells, which is about 1/5 of the tetrahedral mesh, which is the major advantage of this method. Note that this reduction in the cell count is a result of combining multiple tetrahedral cells to form fewer polyhedral cells. The minimum orthogonal quality of the mesh is 0.21, which is also better than the tetrahedral mesh. Additionally, each cell is surrounded by many adjacent neighboring cells, hence resulting in better approximation of the gradients and lower numerical diffusion effects. Now, let's look at hexcore fill-with method. Based on this selection, new user inputs appear in the task. As the names indicate, the min cell length and max cell length parameters control the minimum and maximum sizes of the cells that are created during the volume mesh generation. By default, Fluent automatically calculates these values depending on existing surface mesh of the computational model. However, the user can change these values as required. The hexcore and the poly-hexcore methods follow the octree meshing scheme. In this scheme, discrete values of cell sizes are used, which results in multiple levels of isotropic Cartesian hexahedral mesh. The cell sizes in each adjacent level of the mesh differ by a factor of 2. Next input is the buffer layers. These are the additional layers of Cartesian cells that are created at the transition location before stepping to the next size. By default, the number of buffer layers is set to 2. It is quite easy to see the impact of this parameter when looking at these images. The buffer layers are set to 1 for the image on the left and 3 for the image on the right. In the first case, there is a relatively rapid transition between two levels of the Cartesian mesh, whereas it is much smoother in the second case. The default value of 2 is generally sufficient for most cases. Next, field layers control the gap between the Cartesian mesh and the geometry or last layer of boundary layer mesh when they are included in the computational model. The smaller the number of field layers, the closer is the Cartesian mesh to the boundary surface or the boundary layer mesh, and vice versa, as can be seen from these two images. The gap is filled with tetrahedral elements which act as transition cells between the triangulated surface mesh or the boundary layer prism mesh and the core Cartesian mesh. In almost all aspects, the poly-hexcore fill-with method is identical to the hexcore method, except that the polyhedral elements are created instead of tetrahedral elements. The primary inputs for the poly-hexcore fill method are identical to hexcore method. Here is a side-by-side comparison of the two meshes for our demo geometry. Notice that in addition to the difference in cell type, that is tetrahedral for hexcore and polyhedral for poly-hexcore, there is also a difference in the total cell count and the minimum quality, with the poly-hexcore mesh containing fewer, higher quality cells. The core Cartesian mesh looks nearly similar for both cases. However, the poly-hexcore mesh has some additional advantages because of the presence of poly cells, such as better approximation of the gradients and lower numerical diffusion effects. Based on originally estimated mean and max size of 2 mm and 128 mm, considering the octree meshing scheme, there are 7 distinct layers of hexahedral elements with different cell sizes. At the transition location between levels, the larger cell is split into 8 smaller cells, which is generally referred to as the 1/8 octree transition. This leads to the creation of hanging nodes for the finer cell size layer. As a result, all hexcore and poly-hexcore meshes created in Ansys Fluent meshing are by default non-conformal type of meshes, and hence require the use of an appropriate solver such as Ansys Fluent, which can handle such meshes. The advanced options and the global boundary layer settings can be left at their default values for most of the cases. For more information, please refer to the user's guide. Now that we know how to generate the volume mesh, let's now talk about the significance of the volume mesh quality and how it can be improved. The volume mesh has a significant influence on the accuracy and stability of a simulation. The default mesh quality measure reported in Watertight geometry workflow is the orthogonal quality. It is the measure of alignment between the vectors normal to the cell faces and the vectors connecting cell centroid with face centroids, which is determined with the help of this equation, and also between vectors normal to the cell faces and the vectors connecting cell centroids, which is determined with the help of this equation. The minimum value that results from these two equations for all faces is the orthogonal quality for the cell. It ranges from 0, which is poor, to 1, which is perfect. However, it is highly recommended to maintain it above 0.1. Let us now understand how to check and improve the mesh quality. Read the provided mesh file again. Generate the volume mesh with the default settings for this demo. Once the mesh is generated, Fluent displays the mesh quality value in the console window as shown here. The orthogonal mesh quality is 0.06. As it is recommended to maintain the quality above 0.1, we need to improve the mesh quality, which can be done with the help of an additional task in the workflow. Right-click on Generate the Volume Mesh task, select Insert New Task and click on Improve Volume Mesh. In the Improve Volume Mesh task, the basic user input required is the cell quality limit. Here, the user can specify the minimum acceptable orthogonal quality for the mesh. The default value is 0.15. Let's keep the default value for this demo. Click on the Improve Volume Mesh button. After the Improve operation, the minimum orthogonal quality is 0.151, which is substantially higher than the original quality and is also above the recommended value. Let's summarize what we learned. We discussed the importance of the volume mesh and learned about the different methods for generating the volume mesh. We also understood the importance of volume mesh quality and learned how it can be improved. That brings us to the end of this lesson.